All right, so our next lecture topic, I was planning on covering the particle in a box, but I realized there's one additional topic related to uh, expectation values and operators that I wanted to cover before moving on to the particle in a box, and that is variance and standard deviation of operators and states, or the associated the states represented through their wave function. And this is related to the statistical concept of variance or standard deviation. They're not synonyms, but they're very closely related. The variance and standard deviation of a statistical distribution, or associated with, so either with a continuous statistical distribution or associated with discrete, a statistical distribution described by discrete probabilities. And for those of you who want to see more detail about this topic and perhaps some additional practice questions, I encourage you to check out the associated math chapter in Macquarie. Or I think it's one of the math chapters around chapter 3 or 4. So first we need to come up with a basic definition of variance, a basic statistical definition. First of all, let's talk about the basic definition of a mean of a statistical distribution. So if we have a set of measurements x sub I, or we'll just call them x, referring to all possible values of x. And so we'd have a set of measurements x1, x2, x3, and so on. So x is some sort of, in statistical terms, is a random variable. It has some randomness associated with it. And each time you measure it, you get a different number. So you can think of it as a dice roll, or perhaps some kind of other measurement process. And then the mean is given by, there's different kinds of symbols, different ways of representing the mean. You could use x with a bar over it. That's not usually what we use in this course, but it is something you've probably run across in other courses. So I show that here for completeness. Another, perhaps a little bit more widely used term is mu. Is a Greek symbol that often represents a mean. It can represent other things, but it often represents a mean. And you can either use mu or mu sub x if you want to be a little bit more specific, in case there's multiple things that you're calculating the mean of. So you use mu sub x. Or you could sort of drop the x and use context to tell you what you're calculating the mean of. Anyway, so and that is given by a sum, right? So you have n samples, and so we're going to divide through by capital N, the number of samples, and then we're going to have a sum starting from, we'll just put indices on all of our measurements, starting from 1, so we set I equals 1. We don't have to start at 1, but why not? So from I equals 1 to n of the sum of x sub I. Okay. And another way, in addition to mu representing the mean, we often use, if we're talking about not a set of measurements, but a set of expected measurements, or an expectation value, right, is given by square brackets. Sorry, one of my square brackets doesn't look good there. X, or maybe X sub I. It, dropping the subscript sort of means, the whole range of X values. And of course, there's a subtle difference that that I've mentioned before. There's a subtle difference between a mean and an expectation value. A mean is for you've already done the measurements and you're collating the results, right? You're analyzing the results, whereas an expectation value is if you have a probability distribution, it's what you would expect the mean to be. Okay, so that's me just getting that out of the way. And then if we want to calculate the variance, that is defined in terms of words as, or the expected variance is the expected squared deviation from the mean. And it is often given by the symbol sigma squared. And that also, it's also sometimes, or sigma squared sub x, where we're interested in the variance of a particular quantity x, a particular random variable, or we can say variance that way, VAR of x. And it's probably worth noting that the variance is the standard deviation squared. So based on this definition of variance, we can define it as follows. Sigma squared is equal to 1 over n. So it's an average squared deviation from the mean. So there's a 1 over n, and there's a sum. Xi minus mu. So for each term in this sum, we're subtracting the measurement, the random variable value, from its mean, and then squaring it. If we don't square it, right, this would all end, you end up with sort of averages canceling out, and you would get 0 every time. But since we square this, sometimes xi will be above the mean, sometimes it'll be below the mean, but we square it, so it always has to be positive, and you end up with perhaps a non-zero variance. Okay, and in terms of expectation value type notation, we use the angle brackets. Again, it would be x minus mu squared within angle brackets. Okay, those are my angle brackets. Now, often we won't have access to the set of random variables, and we want to have calculate an expected variance. So we want to move to an expression that is a little bit more general than this, that doesn't require you to have a set of actual measurements, but you could also have a set of, say, population fractions, or a set of probabilities, or a continuous probability distribution function. And so, let's go ahead and derive an expression that we can hopefully, that's hopefully a little bit more general. First of all, let's take our summation and expand it. Okay, so we have x sub I minus mu squared inside that summation, and we could and that x sub I minus u is squared. So let's expand the square, and that's going to give us, we're going to have a equals 1 over n, and then the sum equals 1 to n. We're going to have xi squared minus 2 mu xi plus mu squared. So we've just basically expanded out that square using the FOIL method. First outer, inner, last. Okay, now let's break down these individual terms in the summation. So we can split up this summation. It's going to be the sum of each of these things separately. Right, so we can split up our sums, or we can expand this as the sum and then collect certain terms of it. So let's just collect all the terms from xi squared. So we're going to get this this 1 over n xi squared. Okay, then for the next one, we can actually pull the 2 mu, since that would be present in each term of the sum, the minus 2 mu, we can actually pull that outside the sum, factor it out. So we're going to get minus 2 mu times 1 over n the sum I equals 1 to n of x sub I, plus then this last term, this mu squared term, we're going to have n of those, and then, but we also have this 1 over n out front, and so those are going to cancel, and so you just get plus mu squared without any summation, right? So you can just perform the sum, and it's going to give you back mu squared. Hopefully I'm not skipping too many steps there. For those of you who are comfortable with this kind of expansion, you see this right away, what I'm doing here. Okay, so now let's do some additional simplification. First of all, this we can think of as, that is the expectation value of x squared, where x squared is inside the angle brackets. Okay, so that's just each of those terms squared by itself. Okay, then we look at this term, that's going to give us back mu. Okay, so we end up with x squared minus 2 mu squared, and then this, and so we have minus 2 mu times mu, so that's minus 2 mu squared. Then this last term is going to give us plus mu squared. So one of those is going to cancel, and we get x squared minus, oops, so x squared quantity inside angle brackets, so the expectation value of x squared minus mu squared. Except mu you can think of as also the expectation value of x. So we get x squared minus expectation, so x, the expectation value of x squared, so x squared, its expectation value minus the expectation value of x, quantity squared. Okay, and that seems like a subtle difference, and it looks like these should cancel out to 0, but if you take into account the way each term sort of varies, and the fact that you end up with something that is, if x is truly a random variable and varies from instance to instance, or is governed by some probability distribution function and has a range of values, then this standard deviation, this variance, sorry, is non-zero. So we end up with this expression. This is a standard statistical expression for the variance of some random variable, and it also works for expectation values, so an expected variance. And let's see, how do these actually vary? Let's go back to if we actually think about this in terms of discrete probabilities. The discrete probabilities where we have xi and some associated probability p sub I, or you could think of p as a population fraction. If it's a population fraction, then it's just going to give you the variance. If it's a probability, then it's going to give you the expected variance. Okay, so the variance associated with a particular set of discrete probabilities. Okay, so if we think about these, what does the expectation value for x squared look like? It's going to be the sum over all of the discrete probabilities. Of pi times xi squared. You don't square both of them, so you be careful here. Some things get squared, some things don't. And so you have to sort of put on your thinking caps and not get things mixed up. Okay, so that's the expectation value of x squared. The expectation value of x is perhaps I should have done this first. Oops, no, not squared. See, I just jinxed myself. Okay, so it's that, but with xi not squared, right? So it's just the sum of either the population fractions or the discrete probabilities associated with xi. So one example, let me just briefly interject an example of, say, a discrete variable with discrete probabilities or population fractions associated with it. Let's say we're talking about the age of students in a course, where we're assuming integer age. Okay, and then you can say, oh, well, maybe 20% of the students are, 20 years old, and 20% of the students are 21 years old, and so on. So you get this population fraction for each age, and then without actually adding up all of the individual ages for the students, if you just know the population fractions, you can do this sum and get the average age. Or if you actually know the ages of the individual students, you can sum them all up and divide by the number of students, but that's not, you don't necessarily need to do that, right? This is an alternative expression, and it's a somewhat more general expression in that it allows us to deal with, it allows us to move from population fraction, from sort of just adding numbers and dividing by the number of samples, to population fractions, and then move from population fractions to a probability distribution. Okay, so it's useful that way. Okay, so and then of course when we take that that sum and we're going to, it's should be fairly straightforward to see that these are going to give you different numbers in a lot of cases, right? That that this expectation value of x squared, where the x squared is inside the angled brackets, you square the x sub I, but not the probability. Whereas if you take the expectation value first and then you square it, then you're squaring both the x sub I and the expectation value. Or sorry, you're squaring both the x sub I and the probability. So you're going to get different numbers out in many cases. Okay, and so just bring in discrete probability there for a second. Now let's move on to, okay, so we have this expression for calculating variance, and variance, again, you can think of as the square of the standard deviation expected for a particular probability distribution or a discrete set of probabilities. And you're going to have different ways of calculating the variance associated with some quantum mechanical observable. So now we're moving on to the quantum mechanics of this. Or variance in quantum mechanics. First of all, how are we going to calculate? We can sort of borrow what we've known already from statistics to calculate a variance. So if we have some operator A, and we have some system in some state described by the wave function psi, and we want to know what is sigma squared A for a system described by the wave function psi, right? Where psi is just some general wave function. It could be the wave function of a particle in a box, could be a wave function of a hydrogen atom, something else. Okay, so we end up with three methods similar to the three methods that we had for calculating just the expectation value. So expected variance, so it's going to be very similar, right? So you can think of this as kind of like recapping what we know already about calculating expectation values, but with a wrinkle, that we're talking about the variance associated with that expectation value. And so we're talking about the spread, right? It's a way of talking about the spread or standard deviation of an observable. How much does it vary from particle to particle or from measurement to measurement? So our first method, again, like the case of that we talked about previously for expectation values, is the integral method. Okay, but there's a little bit of a wrinkle here that we'll have to talk about for a second. And so our sigma squared sub a is going to be given by this expectation value for a squared minus the expectation value for a, so first, and then take that quantity and then square it. Okay, so that's, but then that leaves open the question, how do we calculate these individual expectation values? So first let's look at the first term, although it's the more complicated one. In terms of an integral, it's going to look like this. It's going to be an integral, and you remember what the expectation value is for an integral, right? And or sorry, what the expectation value is and how to represent it in an integral. It's basically you make an operator sandwich. You sandwich the operator between two wave functions. In this case, the operator is a squared. And we have some differential volume element, and we integrate this over all space, whatever the space associated with our wave function is, whether that's 1D or 2D, or spherical polar, whatever, 3D. Okay, so then the question is, how do we square an operator? How do we look at a square? Well, basically, we apply the operator twice. In other words, you can think of a squared is a, and that if you insert some function psi, you're going to first apply the first operator on psi. It'll get you back some new function. We'll call it phi. And it may have, phi may contain some constants, it may have an eigenvalue in it, something like that. Or it could have some functions of x, if a is a differential operator. There could be just a different function, or it's turning a sine into a cosine or something like that if it's a differential operator. And then you would apply it again. You apply the second operator, and then that's going to give you some other function. So you have to apply it twice. And another way to look at it, you can sometimes kind of group them together beforehand. So another way to look at it is you can either take the operator, apply it to a function twice, or you can sometimes group things together. For instance, if we look at momentum squared along the x-axis, we can actually see what's going to happen. You have minus IH bar d dx, so it's a differential operator, as we mentioned previously. We also have this, we're going to have two copies of it, so we have minus IH bar d dx. So it's clear that this operator is going to end up taking the second derivative of a function, and there's going to be, we're going to be multiplying it by these other constants, this minus IH bar twice. Okay, so then we can collect terms a little bit, and we know that a second derivative is equivalent to taking a first derivative twice. That's just the way it's defined. And let's see, minus I times minus I, so the minuses cancel. So then you just have I times I, which is minus 1. So I'm going to get minus, right? But there's no I left, right? Because I squared is minus 1. It's not minus I. So we have minus h bar squared d squared dx squared. So that's our momentum squared operator. And you're going to get the same answer whether or not you use this or whether or not you apply this, the momentum operator twice to a function. It's going to give you the same result, right? Mathematically, in terms of calculus and algebra. Okay, so that's how you square one kind of operator. Another, so that's a differential operator. That's kind of the more complicated case, right? The simpler case is something like the x squared operator. That's just going to be x times a function, or just x squared times a function. So it's just, we would just insert x squared into our integral, then perform the integral, and then whatever number we get out, that's our expectation value for x squared. Would be just putting x squared inside that operator sandwich and turning the crank on the integration. Then the other part, of course, is simpler. We also want to calculate a and then square it, and that's just going to be, first of all, we're just going to calculate the expectation value for a, which is just going to be our integral over all space, psi star a psi d tau, and then that's going to give us the expectation value for a, and then we would, after we perform the integral, we would square it. We would square it after we. So you're going to perform this integral, and it's an integral over all space, so the spatial coordinates should be integrated out, and you'll get some number like 7, and or 5h bar, or something like that, and or pi. And then you would just take that value that you get from the integral and square it. I have to remember to square it. It's a little bit there's multiple steps here, and so there's some room for confusion. I strongly encourage you to practice some of these skills. So that's the integral method, or at least an intro to a sort of quick introduction to using the integral method. You basically have to make that operator sandwich. You might have to sort of combine the two operators together to make this sort of squared operator, like I did in the momentum case. Other times it's more simple, like the x squared case. Plug that into your integral and integrate. That gives you a value. Then you subtract this other value, expectation value for a. First calculate the expectation value, then square it. Right, so it makes a difference whether or not the 2 for the square is inside the square brackets or outside the square brackets. It's an order of operations issue, and it's one of those cases where it actually does matter, because in one case you're squaring it first and then integrating, in the other case you're integrating and then squaring, and so it does give you different results because of the way integrals and derivatives behave. Okay, our second method is the eigenvalue method. Right, again, mirroring what we did with expectation values previously. So so this method is not general. So the first method is general, at least as long as we have it assumes that we have some nice functional form for our wave function, and that calculating any derivatives and integrals associated with that is straightforward, and then you can use that method always. Although it may be a very messy integral, so it's good to have some other methods around just in case. But that's our sort of brute force. If you have lots of information about the wave function and so on, and you have complete information about the wave function, and you're really good at calculus, or you let a computer do it for you, or at least have a computer help you. You don't want to hand over all agency to the computer, but if you that first method can be used. However, you don't always have all that information, and you certainly need other methods. And sometimes the integrals are too messy, and it's good to have other methods. And it's a little bit like having, sometimes there's a shortcut, and when it's available, you should take it. And so here's a case where sometimes the shortcut's available, and it's this eigenvalue method. So if we have an eigenvalue situation, like if a psi equals little a times psi, where little a is an eigenvalue, it's just a constant. By the way, the eigenvalues can be 0. That is allowed. It just, 0 times psi seems a little bit kind of undefined, but it's not undefined, it's just 0. And it's what you would expect if your eigenvalue is 0. So 0 times a function is 0. Anyway, so that's something that will come up again later. Watch out for that, just an important special case. Okay, so if this is true, only if this is true, then the variance is 0. This is important. This is telling us now, we've gone through a lot of effort saying that quantum mechanics has all this uncertainty associated with it, but not always. There are certain wave functions and certain observables where they form a pair. They form a they form you have an eigenfunction of that particular operator. When you have an eigenfunction of that particular operator, and the system is in that state, then there's no variability. You have a pure state. Every time you measure it, you're going to get the same value. And it's going to be a value of A. It's not going to be a value of 0. The variance associated with that value, right, the standard deviation associated with that value is going to be 0. So it's going to be A plus or minus 0. So this is the no variance case. And my pen seems to have stopped working here. And next I'll talk about the third method. I'm going to stop this video here and try to deal with my stylus problem.